We now implement the most basic graph traversal algorithm using breadth-first search. And for implementing any of these algorithms, it always helps to store the graph structure as an actual graph. And for that, we use a dictionary in Python. And this could look as follows. For the example we use a dictionary, and then we have a key for each node, and we store a list of children that it has. And in this case, you can go from A to B and C. And I've prepared the other ones already in here. You can go from B to A, back to A, or to D, or to E. From C, you can go to A or to F, and so on. So this is the most efficient data structure for programming. It's maybe not the most efficient for performance, but this will help you to understand the algorithm. Now, if we go and look at the pseudocode, the first thing we need to do is we need to create an empty queue. And for that, I use a list. And in that queue, we want to store all the nodes that have to be visited. And we start with a start node, which is A. And we eventually want to get to the goal F. So we populate the queue with a start node. This is the first node we want to look at, and we also need a data structure to keep track of the nodes that we have already visited. We call that visited. We make this a set, and we add start to it. The reason I make this a set and not a list is because we can check if there is an entry in a list, in a set, in constant time, because it's a hash data structure, very efficient. And now we can go through this queue and say, while there's something in the queue, we want to fetch the first entry of it. We call that dequeuing, and we use the queue and we pop from the left. That gives us a first in, first out data structure, like a queue in a coffee store. If you would just do pop like this, we would implement depth-first search because we would always pop the last in item. So we want to pop from the left instead. And now we can look at the neighbors of V, and the neighbors of V are stored in the graph structure. So these are the neighbors of V. If you put in B here, you would get A, D, and E. So we can loop through those, and now we will get A, D, and E if this were B, but we don't want to visit that again. So we say if U is not in visited, only then we want to add that to our queue. So we can append U. And of course, we don't say is in Python, but we just say if U not in visited. So we want to append it, and we want to have it visited, and we add it to the visited set. So this should be giving us a basic graph traversal. We can look at the nodes as they are actually visited by printing them, and let's run this and see what happens. And indeed, we visit first A, then B, then C, then D, then E, and then F. And if you check the graph that we defined up here, you will see that this is actually a breadth-first search traversal. Now, how do we get the path? We need one more data structure, which we would call parent, and which stores the parent of each node. We make this an empty set initially, and now we keep track of each parent and say, okay, the parent of U has been V, and now we can print all the parents, and we can see what we get. And we see there is already enough information to backtrack a path from F. If I want to go back to A, I first have to go to C. Once I'm at C, I can already reach A, and I have my shortest path. So how to do this? We will traverse this list, and we would say that the current key is goal. And now we can say while the key is in the parent key structure, then I advance it to the next one, So in this case, I start with the key to be F, and F is already in this parent structure, so I will get C. C has an entry in the parent structure, so I keep going, and I set it to A, and then I check again, and no, A is not a key in the parent structure, so the algorithm will terminate there. Now we want to store all of these, so let's create a list of entries for a path and append it. And let's see what we will get. So we get a list C and A. Of course, F is missing because we've never added it, but I also want to get this data structure the other way around. So what I do is insert the key at the left. So now we have the right order, and we want to have ACF, so we just have to add the last node to it, and we have our shortest path from A to F. Now we can try to get a different path, and let's say we want to go from B to C. Let's see if that actually works. And so the path here is BAC. That means we have to go back to A and then go to C. That is the shortest path from B to C. Let's try this with E. And here we would expect that we need to go back to B and then to A, and then we get to C. And indeed, we get the path. Actually, it found a different one. It found one that is even shorter to go via F, and that is indeed correct. Even better. Now, what else can we try? Let's try to go from D to F. And in this case, we have to go from D to B, and then we can go to E and then to F. So this is the shortest path, or the easiest way to traverse a graph and extract the shortest path. We will later look at how to use a more complex graph structure like the one provided by a grid.